Hi, everyone, and welcome to our keynote today on AI and machine learning for next-gen 5G mobile networks. I'm Louis Sciabbala, Senior Director of Marketing at Mavenir, and I'll be your speaker for about the next 20 minutes. I really appreciate you taking the time to listen in. Why don't we go ahead and get started? So my talk today will cover three different areas. I wanted to find a way to talk about AI, not just in the abstract or in conceptual terms, but really key in on how network operators can use the technology to address real-world problems that they're struggling with today. So specifically, we'll start out talking about the RAN Intelligent Controller, or the RIC, and how it can optimize the RAN network. And then we'll shift over to the core of the network, and we'll talk about NWDOF use cases for network automation, optimization, and planning. And then finally, we'll finish up with the discussion about AI for service assurance, service orchestration, and slicing. All right, so here, we just wanted to talk about the significance of AI in our daily lives. What's all the buzz about? We hear about AI in almost every facet of technology. We hear about all the good things it could do. We also hear about some of the concerns that people have with AI. I thought this was a good statement by Sundar Pichai, the Google CEO. You may have heard this before, but Sundar says, in reference to AI, that it's one of the most powerful things humanity is working on, more profound than even electricity or fire, perhaps. That's a strong statement. I'll leave that to you to ponder. However, Sundar goes on to say that anytime you work with technology, you need to learn to harness the benefits while minimizing the downsides. And so for me, I think of mobile networking industry and how AI has impacted it, and I think that the benefits of AI far outweigh the downsides. So we believe operators are facing many challenges, and AI can address those challenges. Operators need to contain costs, they need to increase revenue, just like any other business. Their bread and butter over the years has been connectivity services for decades. So now they need to scale at a fast rate and introduce revenue-generating services, all while keeping customers happy by providing customers with a choice of services and timely delivery of those services to the marketplace. At the same time, they need to keep the network reliable and high performing from a quality perspective. So there's huge pressure for network operators to step it up and do something different. Networks are getting more and more complex due to multiple generations of mobile technology and different types of technology overlapping each other: physical, virtual, cloud native. And then we have new domains merging with 5G. For example, enterprises are now trying to come into the same domain with 5G because of the value of low latency, high bandwidth, edge compute, distributed intelligence. All these things make their network smarter. So this is really where AI shines. It uniquely addresses multiple pain points all at once. So what can we do with AI? Networks are evolving, and AI is being used to assist with network operations, to lower costs, to gain agility in providing services, and to increase the overall user experience. Without AI, we have to rely on manually upgrading the network every year. The networks don't learn on their own. We're working on making AI so much more impactful in this sense. AI can help operators gain insight in how to deploy and operationalize the network most efficiently by sorting out data that really is relevant and using those insights to feed AI and machine learning algorithms to make the most intelligent, automated decisions. AI can be used to figure out how to dimension the network and a plan for capacity expansion and achieve scale. So no longer are the days where network operators have to dimension and plan for capacities at peak or worst case. We can use AI to glean insights and intelligence and to do this in an automated manner. AI could be used to eliminate errors from manual tasks that are done, try to isolate problems before they actually manifest into a problem. I read a report the other day that suggested 90% of mean time to repair metric is spent trying to figure out if there's actually a problem or not in the network. And then lastly, AI can be used to tune the network. So when it's not performing well, you have a closed loop feedback mechanism that can take data real time, understand what's happening, and tune the network so that it operates in a much more efficient manner. So we want to look at AI from a very holistic end-to-end point of view. It's kind of a new intelligent operator backbone, if you will, one that's infused with AI and machine learning everywhere, from RAN to edge to core to applications. Granted, this isn't easy, and this isn't something you can just turn on overnight. To be effective for service providers, we really require deep knowledge of both the telco domain, and also we require deep knowledge from data scientists. So there's still very much the human element that's required in implementing AI solutions. If you look at this chart, there are use cases galore. We think about the network in 4 pillars here, each of them inextricably linked to each other from an intelligence perspective. The intelligent network, or network AI on the far left, consists of capabilities like the RAN Intelligent Controller and the core NWDAF. And here are use cases that help keep the network layer applying its resources in the most efficient way, whether we're doing load balancing or beam control or traffic steering. Next, intelligent operations is all about taking the manual legwork out of analyzing the massive amount of data that's collected in the network, so we can automatically find anomalies and take to some sort of healing mechanism or action before it actually becomes a major problem. These are things like auto root cause analysis, correlation of metrics, anomaly detection, and so on. In the services arena, we know that customers demand high network quality and a personal high-touch user experience. We have tools for this, so we can combine the knowledge that we've gained from services in telco, things like SLA and quality of experience monitoring, combine that with data science knowledge to better cater to the overall user experience. And then finally, we want to look at the intelligent business. So we look at enterprise verticals, and because of 5G, there are new business services coming into play in enterprise verticals. We look at segment like AI apps with computer vision, industrial, IoT analytics, robotics, and AR, VR, where we're addressing business intelligence with pre-orchestrated workflows that are available now. And we have models and rules to address all these new use cases out in the field. So let's zero in on network AI for a moment. Network AI covers a couple different domains in the RAN and in the core. So we have the RAN Intelligent Controller in the RAN, and we have NWDAF in the core. In this segment, AI thrives on big data collected from the network itself. If we're able to democratize data availability and normalize it when we gather it from different domains like the RAN, the packet core, IMS, security, etc., then we're able to really apply some of these models. All the information comes in a unified way from various databases, and the catalog consists of different functions that can be applied in one domain or across domains. Once an AI function is implemented for a given domain, the similar use case can be applied to another domain. So for example, if you have RAM parameter tuning, this is something that you can apply in the RAM, but you can also apply it in IMS. The way we implement this is using transfer learning, and this can be done somewhat easily. So the AI model catalog can be deployed a la carte, or it can be deployed as a package. But the key thing to remember that it's very flexible and it's a very powerful tool for operators. Okay, let's talk about automating RAN operations with the RIC. So a large RAN needs a lot of maintenance. It needs a lot of people, needs a lot of people taking measurements, doing drive testing. There's a lot of paperwork. There's a lot of meeting time. All these things can be automated with AI. The whole process can be applied to algorithms. And an operator can achieve high performance from an existing RAN completely remotely using these AI algorithms. RAN automation has been increasingly gaining significance with every generation of cellular deployment. With 5G, it's not even an option anymore, but it's a necessity from day one. We used to have something called SON. SON was an attempt to automate the RAN operational processes, but a lot of these processes have been offline with back office processing and changes still done during a maintenance window. So this has been a slow process of tuning the RAN clusters, and it's really been one of the impediments of SON's wide-scale impact. The parameters to be configured in a given RAN have been exponentially increasing and will continue to be with 5G, with the network slicing on the scene. All these problems become even more profound. So instead of a maintenance window and a slow offline processing of data, with the RIC running AI and ML-based optimization algorithms, operators can execute real-time parameter tuning any time of the day. We've talked to some operators who have even planned to run a maintenance slice to run optimization campaigns and experiment with new algorithms on a 24/7 basis. Let's talk about AI and the link to openness and innovation. So with 5G, operators have decided to move forward with cloud-native infrastructure and cloud-native architecture. Web-scale companies have offered new applications at a much faster pace than telecom companies have ever done. And because of the open platforms and APIs that have been adopted by web-scale companies, the whole world has been able to innovate on these platforms. So this level of rapid innovation has not been possible on telecom infrastructure so far. The hope and the rationale for telecom is that operators should be able to compete on equal footing with the web-scale companies. As of now, we have had mostly closed systems in the telecom infrastructure, especially in the RAN. Nothing has really been open or multi-vendor in the RAN. Like I said before, SON has had some limited success in introducing non-RAN vendor solutions, but it's still been sort of a black box. So the RIC has been thought of as the next generation of SON in the next generation of RAN. With the O-RAN forum, we have well-defined interfaces, and the RIC is really allowing for open APIs for anyone in the world who wants to run an innovative idea and run innovative applications. They can control RAN behavior. So that, again, very powerful thing. Here, if we look at the diagram, in this reference diagram, we can see a RIC built on an O-RAN specification with new interfaces for both non-real-time and near real-time applications. The near real-time RIC interfaces with the RAN over something called an E2 interface, which is standardized for low latency applications. And the non-real-time RIC, is part of the Service Management Orchestration System, or the SMO, as defined by the O-RAN Alliance. And this consists of a platform plus a set of microservices to introduce intelligence into the RAN. So the non-real-time RIC is intended for long-term data processing and prediction. It collects KPIs and log information from the ecosystem of data from different RAN elements, and it provides AI cutting-edge reinforcement learning tools and algorithms to process the data, make policy decisions, and then takes action into the RAN via the CM or AI interfaces to affect network changes. So we've actually tested this use case and have some pretty exciting discoveries, which I'm going to show you here in a couple slides. First, just take a quick look at this illustration. So in this illustration, we're talking about parameter tuning. And what we're trying to do here is when you deploy a site, you might initially see things like interference, low throughput, high handover rates, all really non-desirable things that you want to see in your network. And this is what we were showing in the yellow circle. And eventually, with the ability from our learning engines, which are based on Bayesian models of reinforcement learning, it's an iterative process. And we take input from the network through KPIs and logs, and we're able to affect change back into the network by sending config changes. And as you can see, the illustration here is that the circle moves from yellow to green. Green meaning good, green meaning we're trying to remove things like interference, we're trying to improve throughput, we're trying to get rid of unnecessary handovers. All these things really is what can run every hour. It could run once a day. It could run as often as the operator would like, but these are algorithms that in the future can run in the cloud and constantly run to optimize the network for the operator and to provide a better overall user experience. So we can actually see some results from this. We've had a tier 1 CSP in this case study that was replacing a legacy RAN vendor with Open RAN base stations. And one of the key concerns that we wanted to measure the performance of the Open RAN and be able to say that it's at least as good as the historical performance of the legacy RAN. So we had a trial cluster of cells deployed consisting of 5 sites with 3 sectors each. And we were looking at performance metrics and KPIs, tracking them carefully over a span of a couple weeks. And we wanted to look at KPIs of high importance to the operator, things like signal quality, channel quality indicators, user downlink, throughput, bad handover, call drop rates, and so forth and so on. So the KPIs here express quantitative measures of coverage, capacity, and mobility robustness. The non-real-time RIC here, equipped with advanced machine learning algorithms, adjusted the configuration of each cell independently while targeting improvement in each of these KPIs. So we compared 2 weeks of data measuring average user throughput. We saw that there was improvement increased by 20%. We also saw a 5.3% increase in the amount of payload that cells were carrying. So in a 15-cell sector cluster of cells, this means we can carry more data. We also improved the channel quality. The call quality indicator on the uplink and downlink both improved. We measured channels with better MCS distribution. This is essentially meaning that the radio can send more bits over the air. And keep in mind, this is a very busy network that's been running for a long time. Continuing on to physical resource blocks, we're using less of them in the cells now. So now we have more capacity to carry more traffic. Lastly, let's look at unnecessary handover. So the service provider experienced a decrease in handover attempts by 57.1% versus similar call volumes. The decrease in handover attempts and the improvement in handover success rate indicates a better balanced mobility profile, which lowered the too early or too late or the ping pong effect of handover scenarios, which in turn had a high impact on the end user experience while also consuming additional network resources. So in this one here, we show a traffic steering use case for near real time. So here we're implementing a reinforcement learning algorithm to do multiple things. In this example, we have calls carried on 2 different layers, a high layer and a lower layer on a given sector. And the operator wants to be able to steer traffic to the correct layer based on the call type. So we have a near real-time RIC using AI algorithms to steer traffic, improve QoS, improve QoE. And we are seeing very good improvement for users because of the reinforcement learning that we've employed in this use case. For NWDOF, we're applying 3GPP use cases, but we also have some unique use cases for UPF selection, or user plane function. NWDOF is a core network element, but we do have an operator in Europe who is using congestion control using a feedback loop with NWDOF. Congestion control occurs mostly in the RAN, but in this scenario, we're able to control congestion throughout the whole network. Architecturally, we have 3GPP exposure functions from 5G core elements. And one of the things we're doing is we are extending that for IP fix and IP flow information from different applications or different network functions. And then we're taking all this and we're enhancing it with visualization tools and input from the data link layer so we can integrate with other parts of the OSS system. Speaking of OSS, the next gen OSS is a complete cloud native OSS for 5G and beyond. So cloud native is a very different concept. We have network slicing put into play now with 5G. We have CI/CD for telco cloud, which requires different layers that are telco specific. We, from an OSS perspective, we are using AI to offer things like zero-click service orchestration, zero-click service assurance, closed-loop automation with dynamic SLA management, and dynamic SLA slice management. So these are all part of the next generation OSS systems that we're able to deploy. And again, when we talk about infusing AI everywhere in the system, Our next-gen OSS system is a big part of that. One large area of the OSS is service assurance. So service assurance with analytics is being enhanced for next gen. We're implementing an observability framework, or OBF, with AI ops, and we're following TM forum guidelines on this. So this is kind of a NWDAF, but not just for 3GPP centric use cases, but rather for the bigger portfolio of use cases that can be used for next generation OSS applications. From a service assurance perspective point of view, we can do things like look at alarms automatically and set thresholds. And we can correlate data between alarms and KPIs. We can have a prediction engine that can do auto root cause analysis to help operational teams. We can do policy tuning. We can do topology management and fault analysis. And we can automatically generate tickets, whether this is in a brownfield or a greenfield type of scenario. One unique application that we're showing here is where we're managing cloud-native functions on one end with a number of clusters on public or private clouds. And we're sending counters, logs, and other types of information to our analytics engine. So on one end, we have existing virtual network functions. Application-wise, these are RAN and messaging converge in the same pipeline with the same way of collecting and providing analysis reports. The unique thing we're doing here is anomaly detection and trend analysis, and we have the capability to add other algorithms to this as well. As of now, this is something that we are in fact deploying with Tier 1 operators. So we've come to the end of the presentation. I hope I've painted a decent picture of how we can use artificial intelligence and machine learning in 5G networks.